Okay, that's good. Now I'll start the recording over here. Okay, great. So let's get the show on the road. So, ladies and gentlemen, welcome to this week's Monsoon seminar. Our speaker this week is Bob Raynolds. He's based in Denver, and in the past he's taught at Peshawar University in Pakistan, in Dartmouth College, at the Colorado School of Mines, and at the Denver Museum of Nature and Science. And he used to work for USGS and Exxon and Amoco. And he is a recognized expert on the Siwaliks, and that's what he's going to talk to us about today. So, Bob, please take it away if you'd like to share your screen. And if you have questions for him, put them into the chat, and I'll call on you at the end of the presentation to ask your questions directly. Thank you.
Great. Thank you very much, Peter, for the introduction, and thank you for the opportunity to join the Monsoon seminar, which has been going on regularly now for what must be the better part of several years. Congratulations to everybody on that. I want to take the time, for me is the morning here, but afternoon for many of you, I suppose, to give a brief overview of the Sawalik sediments in northern Pakistan. And my presentation is really going to be somewhat general. This is work, a lot of the work was that I did back in my dissertation days, which would have been in the early 1980s, was done in conjunction with a team from Dartmouth College in the eastern United States, and we were collaborating with Peshawar University. There was also work being done simultaneously by Yale University in New Haven in collaboration with the Geological Survey of Pakistan. And these collaborations, these international collaborations, resulted in a tremendous amount of research done on the sedimentary rocks in the northern Pakistan area. These are sediments derived from the Himalayas. The team from Yale was primarily interested in paleontology, and they worked on the Miocene section. The workers from Dartmouth College, my colleagues, Gary Johnson and others, were primarily interested in the Pleistocene sediments and looking at the interplay between structural geology, tectonics, and sedimentation. Over the course of the last few years, as many of you know, there's been a lot of interest in looking at the relationship between stratigraphy and climate. And here in the Western United States, we've spent a lot of time looking at the Paleocene-Eocene boundary and looking for sedimentary manifestations of the climate changes that took place in that interval about 55.5 million years ago. And there have been several places in the Bighorn Basin and in the Piceance Basin and perhaps in the San Juan Basin of Western United States where there appears to be a signal associated with climate change in the sedimentary rocks. These are sediments that are filling the Laramide intermontane basins, and there in several places appears to be a pulse of sands that arrive at the Paleocene-Eocene boundary. And the suspicion is being raised that there is a climate signal in the sedimentary rocks. So looking back over my dissertation work in Pakistan, I have been curious to see if there are climate signals preserved in the Sawalik sediments. And by climate signals, I'm not quite sure what I'm looking for explicitly, but I do anticipate that the Pleistocene in the Himalayas and in the headwaters of the rivers that were feeding into the Sawaliks would have been a time of great change, I would imagine, from the preceding Pliocene times. And so it might be that one could ask the question, is there a stratigraphic manifestation of the Pleistocene in the sedimentary rocks at the foot of the Himalayas? So let's keep that question in mind, and I'll go through an expose of what I've seen and share with you the information as we see it, and then consider that question as we look at the data. I'm going to share my screen here And we'll put up first a PowerPoint, and it'll take me a moment. Bear with me here. And I'm assuming now you're seeing what we're never supposed to let people see, which is the whole PowerPoint show. But
That's right.
I hope you see my title slide.
Yes, I can see it.
Perfect. So, you know, the basic setup, as you're all familiar with, is you have the subcontinent plowing into the soft underbelly of Asia, creating the orogenic uplands of the Himalayas, and the Siwalik sediments are deposited in the foreland basin at the foot of the mountains. And the Siwalik sediments extend from Pakistan across into India, Nepal, towards Sikkim. And they're broadly speaking the synorogenic debris or molasse sediment deposited in the foreland basin. The nomenclature gets a little bit obscure if you go to the far west. If you drop across the Indus River, heading down towards the Suleiman Range, the names change a little bit, but the basic framework is similar. And of course, as you can see here on this beautiful National Geographic diagram, the debris ultimately emerges from the overfilled foreland basin and overflows down on the west into the Indus cone and on the east into the Ganges cone in the Bay of Bengal. This is a physiographic map of Pakistan showing Afghanistan as well, and the drainage patterns can be nicely seen emerging from the uplands in the Himalayas, draining down across the Punjab and down towards Karachi. River names here. The Indus, I guess, of interest here would be that the Indus River originates actually in what is now Tibet and China, and flows along strike in a big strike valley until it gets to about Skardu and near Gilgit, and then it drops into the Indus Gorge around Nanga Parbat and comes down into the foreland basin. We'll see a couple of pictures of where the Indus originates here in a minute. In broad strokes, you can see the division between the Indus drainage and the Ganges in a very schematic diagram made a long time ago, before Adobe Illustrator. And you can see the broad catchment of the Ganges, much of which flows parallel to the mountain range versus the Indus drainage, which is pretty much, if you will, perpendicular. Sedimentary rocks accumulate in the foreland basin. The pinker, redder colors are thicker, and a pretty standard model in terms of foreland basins shown here with this big diagram. And when viewed from space, and we'll see several space images here, and in fact, I'm going to try to give a Google Earth tour in a little bit of the Siwaliks, but you can see broadly defined the Indus River defined by the agriculture, irrigated agriculture along the reaches of the Punjab, the 5 tributaries and the Indus itself, flowing down along the Suleiman Range, dropping down into the Arabian Sea. Of course, this is interest today because of the flooding, and I've got a few flooding pictures towards the end of the show just to remind us of some of the current circumstances in this drainage system. The Indus is a powerful river. Here, standing or sitting on the side of the river near Attock, you can see the coarse material being carried, coarse gravels. And if we go to the headwaters of the Indus River, here it is up in the area near Mount Kailas. The Indus tributaries are flowing to the left, to the west, and the Ganges tributaries are flowing to the east. And in principle, Mount Kailas, as recognized by Augustus Ganser a long time ago, defines essentially the headwaters of these giant river systems. Beautiful scenery. If you come into Pakistan, this is the Khyber Pass area. Just again, to give you the feeling of the landscape, pretty arid. The rocks are well exposed. Massive faults divide. In this case, you've got carbonate units overlying flysch with a giant thrust fault, which you can see on the road here. This is the road up to the Khyber Pass. And you can see the thrust fault very nicely on the side of the road, and has beautiful striations on that thrust fault. If you ever get to the Khyber Pass, hopefully someday we'll be able to get there again. You can see this fault plane. Comes down into the town of Tower, an ancient town. Alexander the Great came through here, and commerce still goes on today, much as it has in the past. If we look at the Siwalik sedimentary rocks in more detail, we'll see that they're comprised of alternating sandstones and mudstones. The sandstone beds are fluvial. The mudstone beds represent overbank deposits, and the entire succession, as exposed in the Patwar Plateau in Pakistan, is comprised of fluvial sediments. And these sediments have lots of clues about their origin. Here, colleague Noy John Sticks and my to-be wife, Mary, are examining some of these cross-bedded sandstone beds in the northern margin of the Salt Range. And you can see the paleocurrents indicated by the cross-bedding. Here, these are trough cross-beds, and the current direction would be from the right to the left. And we've done a lot of work on looking at the paleocurrent orientations in these sedimentary rocks, and there's a robust record indicating changes through time of the paleocurrents as the rivers evolved. The strata, as I mentioned, are made up of alternations between mudstone and sandstone. The mudstones would represent paleosols and adjacent floodplains contiguous to the river systems. And the river systems are either single-storied or multi-storied sandstone beds reflecting the thalwegs of the river systems flowing off of the Himalayas. In some cases, you get stacked multi-storied sandstones. A photograph here by Gary Johnson, who's with us this morning. And you can see the sandstone beds, one on top of another, representing the reoccupation of the channel belt by succeeding river systems, so that the channels in some cases are sufficiently constrained by structural features that they stack one on top of another, as illustrated here. Again, Gary's artwork here illustrating schematically the character of the sedimentary rocks, with the multi-storied system on the left and the single-story system right, with the black representing the floodplain deposits. Wide variety of sedimentary features can be observed and measured in these sedimentary rocks. Again, question just to remind us, I was looking to these rocks to see if there was evidence of climate change. And I'll jump to the conclusion and say that it's difficult to see evidence of climate change in the rocks. What we do see is evidence of structural evolution of the foreland basin. The primary tool we use for identifying the age of the rocks is magnetic stratigraphy. And here, Gary is obtaining an oriented hand sample from the mudstone beds beneath one of the channel sandstones. These oriented samples are then cut into cubes, and people use different techniques. You can use a drill system today to get oriented little mini cores. But in any case, your ultimate goal is to have an oriented specimen, such as these cubes, with their field orientation scribed on them. And then they're put into a magnetometer, as illustrated here. We did this at Columbia University, and Neil Updike's lab at Lamont. And the cubes are spun in a magnetometer. They're subjected to either alternating field or thermal demagnetization, or both, and reveal the signature of the magnetic field at the time the sediments were deposited. We end up with a series of stacked measurements. And here you can see a thickness scale in meters, 800 meters of section, with an alternating polarity field recorded in the rocks. And the polarity field can be recognized and fit into a worldwide magnetic polarity timescale. And that can be additionally calibrated by dating volcanic ashes, and in addition by the recovery of fossil vertebrates, many of which have been calibrated themselves. So you can use independent means of identifying the polarity signature as shown in these rocks. And of course, just to make the point, this really is the same tool that we use to recognize seafloor spreading. And here I've got the sketch of Iceland and the adjacent Reykjanes Ridge with the polarity stratigraphy recognized in the seafloor stripes. And I emphasize that those seafloor stripes are the same polarity patterns that we see in the magnetic stratigraphy in the sedimentary rocks in the Himalayan 4D basin. A view of the village of Jhelum, or the city of Jhelum, looking up towards Mangla Reservoir on a beautiful day where you could see the snow-covered Pir Panjal Mountains in the distance and the near vertical sedimentary rocks, in this case punctuated by a volcanic ash, which is the white stripe, which if you can see my cursor there in the foreground on the left is a white stripe, and that represents an airfall volcanic ash with some reworking that accumulated in the synorogenic sediments, and of course allows us to use radiometric dating techniques to amplify and supplement the magnetic stratigraphy. Here's a close-up view of one of the volcanic ash beds, typically with a sharp base and a more transitional top as the upper part of the ash gets reworked into the sedimentary section. These magnetic polarity profiles can be correlated one to another from adjacent areas. And this is the kind of approach we took to work out the stratigraphic record in the foothills of the Himalayas, where in many cases the facies can be laterally changeable or variable, and the magnetic polarity stratigraphy allows you to have a common basis to compare and correlate adjacent rock packages. Here you see 5 measured sections, and they have their original meterage there, and the red little stripes represent volcanic ashes, several of which have been dated, and they all permit us to tie the polarity transition seen in the rock to the worldwide polarity succession shown on the left-hand side. In this way, we're able to date the rocks with considerable confidence, even though there may be absent of fossils, but the rocks can be dated consistently over broad areas, and we can compare and contrast the sedimentary patterns between, if you will, between anticlines, between structures in the Patwar Plateau. This can be assembled across a much broader area. Doug Burbank and his colleagues assembled this diagram, and here you're seeing everything from the Trans-Indus, meaning the area to the west of the Indus River on the left-hand side, through the Patwar Plateau in the center, and heading in towards India and Kashmir on the right-hand side. This is an example of a summary diagram. Many of these have been prepared over the years, and it just serves to illustrate the richness of data that has been accumulated from the Sawaliks. I'm going to step out of my PowerPoint if I can here. I want to give just a brief Google Earth tour, and I hope you can all see Google Earth. And I just wanted to take the opportunity while we're gathered to, let me just set the stage here. Here you see the entire Indus River drainage, and you can see the same colors we saw in one of the earlier PowerPoint slides. We're going to zoom into the Patwar Plateau, which is this feature right here. And I just want to show you the character of the outcrops and share with you some of the basic geographic framework that we're going to be discussing at the end of the talk. The Indus River itself is coming down through Tarbela Reservoir here, and you'll see the Tarbela Dam. The Indus River flows down through Attock and then drops down across the northern part of the Patwar Plateau, coming out onto what's really the Indo-Gangetic Plain as you get down towards Mianwali down here. This feature here is the Salt Range, and the Salt Range is renowned geologically. It has Eocambrian salt deposits that are mined still today, giving it its name. And the salt range is thought to have been formed by décollement on the basal salt deposits, which are exposed in various places along the front of the salt range, as well as in the tear faults here on the west side. You can see salt deposits sticking out. Our area of interest is the Potwar Plateau, which is held up by the salt range, and in particular, the eastern Potwar Plateau. Here we're heading in to see it. The city of Islamabad, the capital of Pakistan, is up here, Rawalpindi. And then a big landmark in this area is the Mangla Reservoir, which you can see here, a big irrigation and hydroelectric project. The folded and deformed foothills of the main Himalayas are shown here on the upper right. And then the eastern part of the salt range, which is a fairly complicated zone of thrusting and folding, revealing a substantial portion of the Sawalik sediments, is present here as a series of anticlines, which I think you can pick out from their vegetation cover. If we zoom in a little bit to look at the sedimentary rocks on the north side of the salt range, you can pretty quickly see this characteristic alternation between resistant ridges and intervening strike valleys. And in fact, as mentioned earlier, this alternation is the signal of this change from floodplain to river channel. And here you can see the character of the exposures on the north flank of the salt range, where you have linear channel sandstones separated by overbank mudstone deposits. And you can quite clearly see the continuity of the rocks over long areas. And many measured sections have been taken in these areas, typically along little valleys that flow through there. And these are what have been correlated over large areas. If we come up over towards the east, the same patterns can be seen. Here we're down in the southeastern part of the salt range, and we have the precursor shelf rocks, which would include the Paleozoic and up to into the earliest tertiary shelf sediments, which culminate in Eocene limestones. And these Eocene limestones are overlain unconformably by the package of clastic sedimentary rocks that come from the north. So a very dramatic facies contrast as you leave the Tethys margin sediments and you are facing with 5 to 7 kilometers of overlying continental clastics that characterize the Sawaliks. Again, I'm trying to emphasize the widespread nature of these rocks and their excellent exposure in the Potwar Plateau. And this has allowed us to study these rocks over broad areas and to make the kind of correlations which I'm about to show you as we come back to our PowerPoint presentation. Just to show the Mangla Reservoir up here, a hydroelectric dam and irrigation systems emanating from Mangla Reservoir. The sedimentary rocks, their deformed character continues across the eastern Potwar, and we have numerous measured sections, again, in these kinds of valley systems where the exposures are relatively good. So we'll back out a little bit. If anybody has any questions, please ask, because we're a relatively small group. So just perhaps raise your hand or shout, and we can amplify. I'm going to go back to Google Earth. Some outcrops of the character of the rock units. Here you see, of course, gravel facies, stacked gravels, which are characteristic of the proximal portions of the Sawalik rocks, well exposed in the area around Mangla Reservoir, which we saw a few months ago. And you can see here a succession of stacked gravels. The gravel deposits are datable, of course, through our previous mentioned paleomagnetic stratigraphy. And here you can see the alluvial fan facies, or the coarse gravel package, prominent in the northern part of the section, and then extending towards the south, it becomes younger in age. And as I'll show in a moment, this represents a prograding facies change, moving from north to south. We can also look at rates of sediment accumulation. Excuse my fauna here. And I'm sorry for the distraction. I think I might have somebody visiting my front door. The rates of sediment accumulation vary and can be measured in many different places. And excuse me for one moment, I'm just going to close this door. I think we'll have more quiet. Anyway, you can see, you can take different measured sections and look at rates of sediment accumulation varying through time. And we have a model illustrated at the top of this diagram where the onset of sedimentation is a relatively slow rate, and then there's a period of rapid sediment accumulation, and then followed by another slow rate here at the top. And the suggestion there is that the sedimentary system is actually undergoing a migration process as the foreland basin evolves, with an early onset of sedimentation, and then a rapid accumulation period, and then a decreasing accumulation period as the sediments, as that portion of the sedimentary basin is approaching the orogenic front. Of course, eventually it's going to be eroded and the cycle will be finished. And you can measure these things across the landscape, illustrating here with the size of the dot, the rate of sediment accumulation, with relatively slow sediment accumulation out in this deformed area here, rapid sediment accumulation in the axis of the, this is a reentrant here, the Jhelum River reentrant, and then relatively slow accumulation on the periphery of that reentrant. So it's very clear to us that the rates of sediment accumulation are spatially variable and temporally variable. The facies are changing. We've demonstrated that. And then the question is, well, what is the control, if any, of climate? And we can look at the rates at which some of these facies changes are taking place. This is the onset of the conglomeratic facies. And if you look at along the axis of the Jhelum reentrant, the rate of facies change is about 3 centimeters per year, which is comparable to the rate at which we believe the Indian plate is moving to the north. And so the facies change rate is reflective of the large scale orogenic changes in the basin. So one of the hallmarks of the sedimentary patterns we see in the Jhelum reentrant and the eastern part of the Potwar Plateau is a control on the general facies characteristics by tectonics and structure, and that seems to be a regional pattern. Another thing that's been recognized over the years, of course, in the Sawaliks are a variety of characteristic facies which give the member names. For example, the Kamlial, the Chinji, the Nagri, the Dokbatan formations. Some of you might have heard those names. Those are reflective of facies patterns that are identified with specific areas where these sediments were originally studied. And there are regional facies patterns and characteristics. The Kamlial tends to be relatively sand rich. The Chinji facies or Chinji formation tends to be relatively mud rich and red colored. The overlying Nagri formation in many places is characterized by an abundance of sandstone, and the overlying Dokpatan and Swan formations would be more the alternations between sandstone and mudstone, as mentioned before. So there are some regional facies patterns in the Siwalik package that extends from, here's the unconformity, the top of the Eocene down here, and then the overlying sediments. This unconformity here is at about 18.3 million years. So at about 18.3 million years, the synorganic sediments landed on the Tethyan shelf sediments at this area. It has been observed that there are, as I mentioned, variable sandstone mudstone ratios or proportions in this package. And again, whether this is a climate phenomenon or some kind of a rate of subsidence or rate of sediment supply from the mountain ranges is a conundrum that has been difficult to sort out. But I will emphasize that the Nagri formation right here tends to be relatively sand rich in many places, not always. And it correlates roughly to the Nahan group over in India, which is also relatively sand rich. And it's approximately 9 to 10 million years old. And it may be that during that time period, there was an increased supply of sediment into the foreland basin for reasons which are not well understood. Catherine Badgley and Turi Serling, Kay Bernsmeyer, others have looked at the isotopic composition of the mudstones and the cankars and the teeth of mammals in the Siwaliks, and have demonstrated in this area a transition from a woodland landscape to a grassland landscape taking place at about 6 million years. This could be argued to be due to climate, maybe an aridification of the landscape, but it is a pattern that is reflected in the isotopic composition of the teeth and the calcareous nodules, not so much in the sedimentary rocks. The fauna in the younger part of the succession in the Eastern Potwar Plateau appears to have a faunal transition at approximately 2.5, 2.6 million years. There appears to be an immigration event. The elephant comes in, the equus comes in, and it appears that there's some kind of a faunal transition, which may be due to an opening of a migration pathway, perhaps from in the Arabian Sea area, so perhaps over towards Iran, but it is not manifest in the sedimentary rocks. The fauna changes, but the local sedimentary rocks don't appear to show a dramatic change at this point. If we look a little bit more closely at the data, the sedimentary rock data from the Eastern Potwar Plateau, here's a geologic map illustrating the strike line configurations of the sediments around the Mangla Reservoir. And our data sets come from within these little boxes on this diagram. And you can see a wide range of places that we've studied, ranging from Rawalpindi and Islamabad, which would be to the northwest, across the Grand Trunk Road, down to the city of Jhelum here. And we've done studies on the Pabi anticline here. We've done studies, as I showed you, on the Google Earth images here on the Eastern Salt Range. And then we've studied a wide variety of the folds in the vicinity of the Mangla Reservoir. And I'm going to be illustrating some of the results of these studies, and again, tied together through magnetic stratigraphy. Here we can look at the Pabi Hills, which are southeast of that, on that southeastern part of that diagram. The paleomagnetic stratigraphy is illustrated in the upper left, and you can recognize the various younger, the Gauss and the Olduvai magnetochrons. That can be turned into geologic time, so we can take the sedimentary rocks as we see them in outcrop, and we can actually calibrate them by millions of years. And here you see the youngest rocks on the periphery of this anticline, and the oldest rocks in the center, 3 million years in the center, less than 1 million years old on the outskirts of the anticline. Likewise, down in the area on the eastern salt range, we looked at, we've done a variety of measured sections in this area, and we can convert this map, which is simply a form line map, to a time map as illustrated here, with the brighter yellow colors being young and the purple colors being old. And so we can build the time frames and then correlate the rocks from one place to another. And it allows us to make diagrams such as shown here, where we've got actually reconstructed landscape. The bottom landscape is 4 million years old, and you come right up to the present landscape at the surface, which would be today's geomorphology. And you can recognize broad changes in what's going on through time. The lowermost panel has the foreland basin with sediments flowing across to the east. As you climb up through time, the conglomerate facies, which is in the reddish color, becomes more widespread. And eventually, when you get up to the very top of the system, much of it is undergoing erosion, with some coarse sediments accumulating in the Milo Reservoir area there today. So we can get a fairly good handle in a series of diagrams like this. We can put it into a block diagram covering a broader area. And you can recognize here the foreland basin floodplain sediments, the alternating sandstones and mudstones, with the arrival of the conglomerates, as mentioned a couple of times here, proceeding at about 3 centimeters per year. This diagram, put together with Doug Burbank, uses his work on the Kashmir Basin to illustrate the sediment in the piggyback basin on the backside of the Pir Panjal Range, simultaneously with sediments accumulating in the foredeep of the Himalayan system. Likewise, on the backside, on the left-hand side of the diagram, heading back over towards the Peshawar Basin, again, another piggyback basin in the hinterland. The diagram, again, illustrates the significance and importance of broad structural features, tectonic features, guiding the character of the sedimentary rocks. We can put this into plan view, and you can see this is a diagram illustrating the Chenab River, illustrating the facies accumulating today in the Chenab River, tributary to the Indus. You can see the sort of reentrant focusing the massive multi-story sandstones, and then thin sandstone adjacent to that, and then the conglomeratic facies that progrades along the top. If we put that into a time diagram, again, it mimics it, and you can see the development of the foredeep with the focusing of the multi-story massive sandstones and the thinner facies off to the periphery, culminating in erosion as the system evolves through time. And I just want to sort of pause here and say that from a stratigraphic point of view, we recognize these large-scale changes, and the large-scale changes that we see are tied to the evolution of the river systems, and the river system evolution is largely dictated in the work that we've done by the evolving structures associated with the Himalayan mountain front. Consequently, the signal, if any, of climate is overwhelmed by the signals of tectonics and structure in the area that we've studied and with the tools that we've used. So the answer to my earlier posed question about was there or is there a signal of the Pleistocene time, the Pleistocene climate in the Sawalik sedimentary rocks, the answer remains elusive to me. It may be there, and it may be that there will be a technique that can be used to pull it out. But from my work, the primary guide to the facies patterns in the Sawalik sedimentary rocks is the evolving structural evolution of the mountain foreland. And climate signals, if there, may be muted. I wanted to finish up the presentation with just some discussions about the monsoon to try to pay homage to the general theme of the session here. And of course, it's an extremely timely situation with the situation in Pakistan today, as many of you know. And I just wanted to show this is a monsoon precipitation map, and you can recognize the blues are high precipitation associated with the summer monsoon in this region. And Pakistan over here typically receives relatively little moisture. Much of Pakistan is arid, as you know. Baluchistan is relatively arid. And if you come across in Afghanistan, it's very arid. And even there's a rain shadow here on the north of the Karakoram, relatively arid. But this is always the case. This is the 2010 precipitation pattern that resulted in the massive flooding of the Indus in 2010. And you can see the big monsoon precipitation concentration up here in the northern reaches, up in the vicinity of Peshawar in the north. And of course, that massive amount of precipitation resulted in a flooding of the entire river system that carried the water downstream, creating disasters all the way down towards the Indus Delta. This is a map of that flooding in 2010. Today, in August of 2022, the precipitation was focused down in Sindh. And this is a precipitation map that comes from the Washington Post. And you can see the massive rainfall in the area here near Larkana. And the Indus River was already in flood, having received flood waters from the Swat and the Kabul rivers. So the river was already running high. And then you had this massive rainfall associated with the unusual monsoon patterns this August, where it rained heavily in what otherwise is relatively arid ground in Baluchistan and in Sindh. And of course, the resulting flooding, which has been so catastrophic and which is influencing Pakistan today. This is a situation that's still going on today. And you can see the extensive flooding in the lowlands here north of Larkana, heading up towards even Quetta. Quetta received damaging floods, which is Quetta is typically very, very arid, as many of you know. And of course, that flood system has spread down throughout the entire Indus system down towards Karachi. And it's damaged agriculture in ways that can only begin to be measured. Much of the agriculture is relatively modestly handled here. This is a typical scene from the Patwar Plateau, planting grain. This was the reservoir in Quetta. I visited Quetta about 5 years ago. Quetta is usually very dry, and now Quetta has had massive floods, and those floods have headed down towards the Indus. And my last slide, just to sort of point out the irony of the challenges being faced in Pakistan today. This is a view in Karachi of the tanker trucks. This was 3 or 4 years ago. And the water system in Karachi has been failing, and water is a constant challenge for the population of Karachi. And these water tankers travel around Karachi delivering drinking water. And it's often said that the driver is heading for your house to bring you your water supply, but if he gets a higher bid or offer, he might be deflected. And so people tell me, well, the answer to that is you send your person to go sit with the truck driver with a few extra rupees in his pocket, and if someone offers a better price, your man is right there to top the bid so that the tanker comes to your house and you get your water supply. But it's one of the great ironies facing Pakistan today that they're suffering from this unprecedented flood system associated with the monsoon rains. At the same time, the water supply in Karachi is problematic. And this is one of the great challenges being faced by the country today, and where a better understanding of the monsoon would be of supreme value to the country, to the people of Pakistan. And it's the kind of thing that I think that organizations like yours, Peter, and others could offer support to the extent that there could be better prediction of monsoon patterns and a better understanding of the impact of changing climate, changing temperatures on the variable monsoon rainfall patterns. And maybe to tie it up, our work in the Sawaliks, which represent the sedimentary rocks extending back from the Miocene up into the really up to the present, we have to imagine that the monsoonal patterns were active in the past as they are today, and that much of the precipitation components that contributed to the fluvial systems in the relatively recent past are similar to those that are active today. So the flooding of the Indus that we see today, the massive transportation of sedimentary material down into the Indus cone through the floods of today are patterns that were probably present in the past as well. And with that, maybe we can turn it open to discussion. If people have questions, or if we want to see anything in more detail, we have an opportunity to do so right now. Thank you all.
Thank you, Bob. Yes, so we do have questions. We have one from Kasim Jan. Would you like to ask your question? I can do it for him if you like. He wanted to know, what is the source of the ash bed?
So I didn't, let me see if I can read it. Is it in the chat?
Yes, it's in the chat. He just wants to know where the ash, the volcanic ash in the foreland basin, where does it come from?
Okay, so actually that's something that Gary Johnson has worked on, and Gary may choose to comment here, but there's a location in Afghanistan called Dashti Nawar, where there are volcanic centers that are of the appropriate age, and we anticipate that the wind directions would have been somewhat similar in the past. There would have been wind flow from west to east, and we speculate that the Dashti Nawar volcanics produced the ashes that fell into the Sawaliks as we see them today.
Thank you. Dr. Baral, do you want to ask your question?
Okay. Yeah, it's evening in Nepal, so I would like to say good evening to everyone. My question is, I'm also working in Siwalik section in central Himalaya, and I'm doing UPB geochronology. And I found that there is some drastic change in the time of deposition of middle Siwalik attained 9 to 10 MA. So I thought that there might be some activation of the major thrust system in Nepal, like in Himalaya at that time. So in your presentation also, I saw that in Nagri formation, you marked that there is some change, which is about the age of 9 to 10 million years, that is dominated with the sand-rich sediments. So is there any relation, like the activation of thrust system that might change the sediment source at that time?
So yes, Dr. Baral, I think that that's a very good idea. I think that if we better understand the timing of motion on, for example, the main central thrust or other massive thrust faults within the broader Himalayan region, it may be that we find that there are correlations between the timing of movement of thrusts and the changing sediment supply into the foreland basin. And certainly that time period that you're mentioning, about 9 million to 10 million years ago, is a time where both in Pakistan and in India, there is suggestion that there was a very large volume of sand delivered into the foreland basin, the Nagri and the Nahan facies patterns. And so that would be, again, a potential structural link to facies patterns in the foreland basin. I think that that's a very, very good idea, and I'm eager to hear more of your research.
Thank you, Bob. And then my next question is there any like continuation of that ash bed in other section, or you just found in one section of your study area?
Well, the Nahan sandstone or the Nagri sandstones in Pakistan are not monolithic, and I have not studied it specifically, but I've looked at many of the measured sections, and the Nagri facies is very distinctive where it is defined, but as you move sideways, the sandstone the proportion of sandstones in some places diminishes. So I think that more work is needed, definitely in Pakistan, more work is needed to define the focus of sand accumulation during Nagri time. And it would not be a very difficult study because so many of these sections have been calibrated and documented. And this is something where field work is needed today. Field workers are needed today in the Patwar Plateau and adjacent areas to take the calibrated paleomagnetic stratigraphy and to try to address some of these questions. And a lot of that can be done simply by tracing the beds and looking at the distribution of the sandstone. It could then be complemented by, for example, heavy mineral studies, which could be used to work on provenance questions. Again, the kind of work that could be done by students today in Pakistan, and then extending across into India and into Nepal. So I think that some of these questions are ripe for young people to work on, and I hope that some of this research can be carried forward.
So I think in this aspect, then we can work with Professor Kashim Jan. So he's so kind person, and then maybe in near future we can work together and to correlate those Pakistan, Nepal, India, and all those like 2,400 kilometer range, and then make a good outcome for the scientific community. Thank you, Bob, for a nice presentation and
yeah, no, absolutely. I mean, Nene, I mean, it's important to appreciate that the rocks do not know the political boundaries. And so here is an opportunity for all of us to work together across political borders and to recognize that there will be patterns that can be identified as in the Indian Ocean as well. And Peter and his colleagues are working on the Indus fan. Other people are working on the Bengal fan. And in time, there will be a recognition that the systems speak to each other. The marine system will speak to the continental system. The systems in Pakistan will speak to the systems in India and Nepal. And together, all of these rock units, the sedimentary packages, will reveal the history of collision, uplift, and erosion of the Himalayas. And the data are lying there waiting for us to read the story from the rocks.
Yeah, it's a good idea. And then we all Siwalik people can work together and make a better outcome for the scientific community. Yeah, thank you.
Yeah.
So can I ask Gary Johnson? He wanted to say something about the volcanics.
Sure, thank you. The question that came up concerning the character of the volcanism, that seems to punctuate the Sawalik record occasionally. The work we've done has identified about 18 separate eruption events, the earliest of which is at about 3.6, 3.5 million from the Dasht Nawar area of central Afghanistan, just west of Ghazni, south of Kabul. And the most recent is just shy of about 1.6 million. So roughly a 2 million year record that is punctuated in various manifestations throughout the upper Sawalik sequence, certainly in Pakistan. And we have found a couplet that is astride the Gauss-Matayama magnetic boundary, which is at about 2.6 million, 2.58. That couplet we can trace as far east as about 30 kilometers east of Chandigarh, India, in the Punjab reentrant. Earlier than that series of 18 volcanic events, we have a couple ashes that one is at around 9.3, somewhere in there, and there's one that's a little bit more than 13. again, on the north flank of the Sawalik, which is where we found them, but we do not know the sources of those, and we haven't done geochemistry on any other, perhaps cinerogenic volcanics that may exist somewhere upwind from those localities at that time. But certainly the Pliocene, Pleistocene volcanic events that we see have helped us greatly in sort of pinpointing where our magnetic polarity boundaries are. And certainly for that 2 million year episode of activity that seems to dominate the Dasht Noir area, it was very, now some recent work was done up there looking at the lake sediments itself in the Dasht Noir, which is about 12,000 feet. It seems to be a collapsed caldera complex looking for lithium. And obviously lithium brines is the big thing right now for electric vehicles and so forth. But the only additional material that was discovered in that expedition, which was conducted in the 2010 to 16, somewhere in there, is a series of resurgent domes, a huge field of obsidian, and some hot springs. So the area is still tectonically or volcanically active in a sense, but seems to not have had significant explosive activity over the last, 1.5 million years or so. Mm-hmm. So, Kazim John, hello, how are you?
Thank you. Thank you.
So actually, I have a question for Bob here. So he said something about there being a muted climate signal, and I wondered sort of why you say that.
So I started this project a long time ago. When I did my dissertation, I was looking at the influence of structure on stratigraphy. Mm-hmm. And then over the many years, we've recognized that climate changes dramatically. And of course, the Pleistocene is a fundamental change in climate. The very definition of the Pleistocene has to do with ice ages, particularly in the northern hemisphere. And so retrospectively, I asked myself, can I see the Pleistocene in the Sawalik rocks that I worked on? And the title of my thesis has something to do with the Pleistocene evolution of the Sawaliks. And so I re-looked at the measured sections and the diagrams that we'd made over the years. And I was asking myself explicitly, was there some way to tease out a change in stratigraphic patterns associated with the transition from the Pliocene to the Pleistocene at around 2.5 million years ago? And Peter, to my frustration, the answer is at least it's not obvious. And I think that the problem is that we are in an area that is so dominated by large structural changes that the signal of structure is overwhelming. And the facies patterns are controlled by structure, not by subtle changes or even not so subtle changes in climate. But that is it remains a testable hypothesis. I mean, I offer it to the community to say, well, are there other places in the Sawalik package where climate might be better recorded? Are there other tools that could be used to gauge it? Are there other ways that I have not yet thought of where someone could step in? And I could bring this right down into the marine environment and say, well, it would be interesting to ask the question in the Indus cone or the Ganges cone, does the Pleistocene manifest itself as something different from the earlier Miocene and Pliocene times? And is there some kind of a change in the character of erosion and deposition associated with what I presume would have been enhanced glaciation associated with the Pleistocene? So I'm posing more questions than I have answers.
was I guess I was curious to put it the other way round. Both you and Dr. Burrell talked about something exciting happening tectonically at 10, but we don't know that's not the monsoon.
Right. So you
Faster
broke up,
erosion doesn't have to be more thrusting, does it?
yeah. You broke up a little bit, Peter, but I'm inferring your conversation to do with the onset of the monsoon. And I think there's a huge question in the community about, when did the monsoon proper become established and what is its manifestation in the rock record, if I can place it so bluntly. And then to looking at Mukhtiar's question in the chat, he's posing the question about the character of the 2022 monsoon. And he points out that the monsoon was extreme both in northern Pakistan as well as down in Balochistan. And the question, again, to the broader community would be, how can we better understand the modern patterns of the monsoon, not to mention the antecedent patterns? And are there ways in which the monsoon structures can be quantified and predicted in such ways to help planners as we look at going forward? I mean, the question that has to be on everybody's lips in Pakistan is 2022 the new normal? And was 2010 a precursor, and 2022, is that the new normal or not? And I don't, I think that we could draw on additional skill sets to try to answer those kinds of questions. But clearly the evolution of the monsoon has turned into a question of transcending importance. I mean, it might have been somewhat academic importance a few years ago, but today, understanding the monsoon is of paramount importance to the peoples living in South Asia.
Yes, agreed.
Yes.
So
Comment, if I could. As we begin to look at Asia in general, the aridification of Central Asia is clearly linked to the development of the monsoon, and that in turn is responding to the uplift of the Tibetan Plateau and the Himalayas in general. And so if we want to find a signal about the initiation of the South Asian monsoon, it's always been there, but it's penetrated historically. When I say historically, probably back in the mid-Miocene to earlier, penetrated well into Central Asia. And so what we have to look at now is sort of the geology of some of that synorgenic sedimentary record in the north flank of Tibet, in the periphery of the Tarim Basin, and to see what the synorgenic clastic record there seems to suggest about an onset of aridity in Paleosol records. And to me, that sort of would then backtrack towards South Asia and saying, all right, this is when the monsoon actually no longer made it into Central Asia and is now constrained to sweeping itself along from Bangladesh all the way to the northwest. It's taking a couple month time to do that, and ultimately end up in the Indus Basin. So, I think maybe Bob and others that have looked at the Paleosol record in the Siwalik could see that there is a signal somewhere, but it's going to be kind of early on about when the onset of the monsoon took place without benefit of having information from Central Asia. That's where it's a critical factor right now, I think. And if I was going to get back on my camel and try to go somewhere, that's where I would go to see if I could look at contemporary sediments and it's been done by some folks at Stanford, contemporary sediments to the Siwaliks, and see what we can come up with. Thanks.
But I think it underlines the fact, though, that paleo precipitation is a hard thing to measure. And I think that it may be that the community could be encouraged. And I think, Gary's pointing out that paleosols could be indicators of aridity that reinforce our studies of paleo aridity, and then link together studies done both in the Tarim Basin, for example, as well as in other parts of the larger system. And I have to say that my work in the Sawaliks has led me to recognize the importance of rivers and the interplay of different river systems, but the amount of precipitation is something that is hard to tease out of the rock record. We can certainly see where rivers go, and we could quantify maybe to some degree how big the rivers were in the past. That might be something to be worked on more. But to understand rainfall patterns in the past is very difficult.
Okay, well, given the time, perhaps we should wrap this up now. Perhaps you could join me either online or using your reaction button in Zoom to show your appreciation to Bob for his talk. Thank you. And I would also encourage everyone who can to come back next week. Next week we have a talk. The talk will be back on Wednesday as usual, and the speaker is Dharmendra Pratap Singh, and he's going to be talking about a new perspective on the Indian monsoon and related processes during the late Quaternary. So, of course, if you're in the wrong time, it'll be in the earlier time slot next week. If you're in a inconvenient time zone, of course, you'll be able to watch it on YouTube later or through Zoom if you don't have access to that. But in the meantime, thank you very much, Bob, and thank you all for coming. Take care, stay safe, and I'll see you all again before too long. Bye-bye for now.
Yep. Thank you all.